So here's a problem that will appear on the exam with regards to computation. Can you guys hear me in the back? Can you hear me, Michael? Yeah. All right, so I'll give you this equation. Okay. This is very similar to an equation that we did in test 1, but this time it's going to be rate constant at a specific temperature. So a certain first order reaction has rate constant 1 times 10 to the minus 3 at 25 degrees. So I'll call this rate constant K1 at this temperature T1. And then the rate constant will increase with a new temperature. So they increase the temperature from T1 to T2. And when they increase the temperature, we have a new rate constant K2, so they want the activation energy. So just as a reminder, the activation energy is the hump. Okay, it's the hump. So energy on the y-axis, and then the progress of the reaction on the x-axis. Having some issues with my projector here, so this little energetic hump is called the activation energy. Okay, whether it's an exothermic reaction or an endothermic reaction. Okay, this would be an endothermic reaction. This would be an exothermic reaction. EA is the energy required to get to the transition state. We'll call that TS. All right, let's go back to this problem here. So this is just plug and play. Plug it in and then get the answer out. So we have natural log of K1, which is 0.003, 0.001, excuse me, 1 times 10 to the minus 3. And then K2 is 0.0035. Okay, we need to solve for EA, which is called the activation energy. Okay, R will be given to us on the exam. It's a constant, 8.314 joules. If I put joules over mole Kelvin in the denominator, the mole Kelvin go up in the numerator, but I'll just put it like that. 1 over T2. So T2 is 45. We want to convert that to Kelvin. So how do we convert this to Kelvin? Add 273. So that's 318 Kelvin. Minus 1 over T1. 1 over T1, what's 25 degrees into Kelvin? 298 Kelvin. So all we have to do is in this problem is solve for activation energy EA. All right. So here's how I will do this. Okay, I'm going to do this natural log 0.001 divided by 0.0035. So this is how you'll do it on your calculator. Okay, 0.001 divided by 0.0035. Okay, natural log it. Okay, natural log that fraction. And you get minus 1.25276. I'll just put some extra digits here. All right, I'm going to do 1 over 318 minus 1 over 298, and I'm going to take that answer from my calculator, take that calculator output, and divide it by 8.314. Okay. So 1 over 318 minus parentheses 1 over 318 minus parentheses 1 over 298, close those parentheses, equals this number. Okay, this minus 2.1105 is equal to this, divided by 8.314. Negative 2.53384, okay, anyways. Negative 2.53850 EA. Okay. EA. Right, so our EA here is going to be negative 1.25276 divided by negative 2.53850. Okay, I'm going to put the units later. Okay, so we're going to have to put our units later in the problem. So negative 1.25276 divided by negative 2.53850. 0.494 joules over mole. Okay, so this is the answer. Alright, so this is a plug and play problem. Plug it in and get the answer out. Okay, make sure you know how to do the correct calculation on your calculator, and then the units for activation energy are joules over mole. Okay. Any questions or comments on this? All right. Is my calculation okay, Allison, or getting something different? I'm getting the feeling I may have done this wrong.
Yeah, I just keep getting
1, 2, 3.
0.000211, like for the 1 over the degrees, the temp. It's like 2 point something times 10 to the negative 5. That's what I'm getting. I don't know what I'm doing.
Minus 2. Oh, I forgot the exponent. Okay, is this what you got? Yes. Oh, okay.
Negative 2.11 times 10 to the negative 4 is what I got.
Yeah, that's what I got. Negative 2.11 times 10 to the minus 4th. Okay. Okay. Right, so make sure you do this on your calculator properly. You know, I made that mistake here. 0.001, let me double check. 0.0035, and that's why I have people who check my calculator. Negative 1.5. Okay, this looks to be okay. Okay, so now we're going to take this. So I did this, take this fraction, and we're going to divide it by 8.314 and get minus negative 0.15068.
For the left side, when we take the natural log, I also got 0.285.
So did you do 0.001 divided by 0.0035 and then natural log that?
Well, I didn't take the natural log yet, so hold on.
Okay, yeah, so that should be the right answer. Yeah, I messed up on this fraction. I probably put in the wrong number. So you take that fraction and then divide it by 8.314. And then let's see what we get now. 1 divided by 318 minus 1 divided by 298 equals this, and we'll divide it by 8.314, and we'll get that. And we'll get this answer. Okay, negative fifth. Okay. And I'm glad I have you guys here checking my calculator. And then we'll take that divided by negative 1.25276. Okay, we'll flip it. Okay, this sounds much more like a right answer. Okay. Oh, come on.
Can you scroll up and maybe show your...
Yeah, this is the answer I'm getting. Which actually, to be honest, sounds more like the right answer. This sounds too small to me, just by my instinct and my gut. Yeah, usually these are large numbers, so you're right. So this is correct. So I think I'm more confident in this. 49,300 joules over mole. Okay, you can also divide it by 1,000, 1, 2, 3, and get 49.3 or 49.4 kilojoules per mole. Okay, so this is our answer for the activation energy. So make sure you do your calculator. See, I set it up all correctly, but then I just put some wrong numbers on my calculator, and it was some astute students that double-checked my calculator, and then we got the right answer. Right, so something like this on the exam. I think for me, I'm going to study, personally, when I take the exam, I'm going to study this. Okay. At least I'll study how to use the calculator. And you're right, Asia, this is more of the right answer. Because when I saw this, I was like, that's weird. That doesn't sound right. Just the number, the size of the number doesn't sound right. So this sounds right. Okay, 49,000 just sounds like an appropriate number, an appropriate magnitude for an activation energy, or 49.4 kilojoules per mole. All right, are there any questions on this? All right, so problem like this on the test, but just different numbers. Okay, be capable of calculating the activation energy using this equation. This equation is called the Arrhenius equation. And it's just plug and play. All right, let's go over a couple of more problems on the test here. Okay, any questions? All right, I'll have this scanned and emailed to you guys on campus. So. All right, so we want to be cognizant of the units of K, which is the rate constant. Okay, this is K, which is called a rate constant. All right, so the units are going to be different based upon whether it's a zero order, first order, or second order reaction. Okay, zero, first, or second order reaction. So basically, the reaction rate units. Okay, we're talking about, how fast a reaction is going to proceed. Okay, so usually it's going to be some concentration over time. Okay, the concentration units in chemistry are in molar, that's concentration, and the SI unit for time is seconds. Okay, seconds. So this is how fast a reaction is going to proceed. Okay, this has nothing to do with the rate constant. Okay, but if you have a first order rate constant, first order rate constant units. Okay, let's say the reaction is A goes to B. A goes to B. let's first do zero order. Okay, zero, first and second. Okay, so remember what our rate law is for a reaction of A goes to B. Okay. Rate is equal to K times the starting material. The starting material here is concentration of A raised to the power, the order. But let's say it's zero order. Okay, so it's zero order. So what is anything to the power of 0? 1. Anything to the power of 0 is 1. So rate is equal to units. I'm just talking about units. Okay, very clearly here. Okay, we're just talking about units. Okay, but what do we know? What are the units of a reaction rate? Okay, molar over second. So for a zero order, the units of K are going to be the units of the rate, which is molarity over seconds. How about a first order rate constant? Okay, units. Okay, so same reaction, A goes to B. Okay, here, just as we've done before, rate is equal to our rate constant times our starting material raised to the order of decay. Okay, if it's first order, this is going to be 1. Okay, so what's anything to the power of 1? Okay, what's anything to the power of 1? It's just, that number. So what are the units of K going to be here? Okay, so what did we say the units of reaction rate were? It's some concentration over time. It's not miles per hour. Okay, and if we're driving a car, it's miles per hour. But if how faster your reaction is going to go from reactants to products, it's molarity over seconds. We want to find the units of K. And what are the units of this concentration bracket? Okay, big M. Okay, remember, this is important. This means M. All right, so we will solve for K now, which is the units. So I'm going to move the K down. Okay, and then molarity over second, I'll move the big M down. Okay, the big M cancels. And then what are the units for a first order rate constant? Okay, for A goes to B. Okay, it will be 1 over seconds. Okay, which is the same thing as seconds to the power of -1. Just units. And then finally, there's a second order rate constant units. Okay, let's do the same reaction. A goes to B. Okay, so we know the rate law, right? Rate is equal to your rate constant K times your starting material, K raised to its order. But if it's going to decay with second order, okay, that will be 2. That exponent will be 2. This is second order. All right. So what are the units of the reaction rate in general? It's how fast a reaction occurs is how much concentration over time is getting converted to product. So molarity over seconds. equals rate constant K. Okay, what are the units of this concentration? Okay, that bracket means M, but it's squared because this is second order, so it's M squared. So K, let's divide by M squared. Molar over second, M squared. So K is going to equal to, one of these M's will cancel out with one of these M's. It's going to equal to 1 divided by molarity seconds, 1 over molar seconds. So that's the unit for a second order decay for the reaction A goes to B, in which A decays with second order kinetics. These are the units of K. Okay, this is also the same as n minus 1 second minus 1. All right. So for the reaction A goes to B, the reactant, if it's second order, you only have one reactant, and that's A. If it's second order, these are the units of K. If A decays with first order, these are the units of the rate constant K. And if the reactant decays with zero order, this is the units of rate constant K. Okay, everyone get this? This is for this reaction. Okay, it will be totally different units if we introduce a second reactant. Okay, and that's a totally different problem. Okay, totally different units for K if it's zero order, first order, or second order. Different reaction, different units of rate constant K. So just something that you can know for the exam. Okay. All right, I'm going to move on here. And there's a half-life problem. Okay, so we'll do a half-life. So this is just plug and play. Okay. The half-life. So for a first order reaction, half-life is natural log of 2 over K. So let's say you have your T1/2. This is just simple, doing your calculations. Let's say the half-life of something is 120 seconds. Okay. Do you remember if this is first order or second order or zero order? Okay. So on your rate law sheet, if you look at it, it's first order. This is the half-life equation for a first order decay. So a half-life equation for a first order decay does not depend on the starting amount. You can have a lot or a little. The half-life just depends on natural log of 2 over K. Okay. So in this problem, let's say you have your half-life is 120 seconds. Okay, what is rate constant K? It's first order. Okay, you can look at your rate law sheet to know that it is indeed first order. Okay, here's the equation given to you. And just like the other problem we did, this is just plug and play. So half-life is a time. Okay, so a lot of students get this wrong. It's a time, but it's a time for what to happen? Time for what to happen? Okay, so 120 seconds is the time for this to be 50% decayed, okay, which is half-life. 50% of the material has decayed. 50% of the material has decayed. Okay. So for first order, this is the equation. For zero order, it's another equation. For second order, it's a totally another equation, so you don't have to memorize that. Okay. And this is just plug and play once again. So we'll put in our half-life here. 120 seconds equals natural log of 2 over k. So we'll just solve for k. All right, so same type of problem, but different number. So what's natural log of 2 over 120? 5.78 times 10 to the minus 3 inverse seconds. You can just plug it in and get it out. Okay. All right, so similar problem on the test. Okay, so this is for first order. Okay, what about a similar problem, a half-life, but it's second order? Okay, let's do a problem like that. So again, you do not have to memorize this. It will be given to you. Okay. Okay, this would be a second order decay. That would be the half-life. Okay. So we'll just plug and play again. This time, what's the difference between the first order decay and the second order decay? Okay, the difference is that this decay, this decomposition really depends on how much you start off with. Okay, it depends on how much you start off with. So let's say we have a half-life of 15 minutes. I'm just throwing numbers here. Okay, so your numbers will be different for the exam. And our starting amount is 0.015 molar. Okay, so question is, what is rate constant K? Okay, it's the same question as up above, but this is a second order decay. Actually, let's just, okay, that's fine. I was going to say, if first order has a half-life of 120 seconds, okay, what would be the half-life? Same half-life, but it's second order. Okay, but the thing is that you need a starting material. Okay, this depends on the starting material. This depends on the initial amount. Your first order decay doesn't. Okay. Right, so this is just plug and play. Okay, plug the equation in to get our rate constant K. Right, so our T1/2, which is a half-life, time in which 50% has decayed, is 15 minutes. 1 over K, 0.015 big M. Okay, so just be cognizant of your units. And then we will solve for K by taking the 15 and moving it down and putting the 15 up across this equation. And then we are getting 1 over 15 minutes times 0.015 molar. And this will be your answer. 1 divided by 15 times 0.015. Okay, 4.444. Okay. Okay, molar to the -1, minute to the -1. Okay, or you can say 4.444 divided, put the molar in the denominator, minute in the denominator. Okay, so this is the answer you would get. Okay, if it's a second order decay, different half-life, but you notice here you really need, it's dependent on initial conditions. It's really dependent on how much you start off with beforehand. So those are the two types of problems involving half-life and decay. All right, let's do a Q problem. Okay, do you remember Q? Okay, Q is what's called the reaction quotient. And let's go ahead and do that problem. Anybody okay? Okay, Q. Okay, so similar type of problem, but just different numbers on the test. Okay, so here's the equation, one equation that you can see here. So here this problem involves the reaction quotient. Okay, this is called Q. Okay, we use Q to compare to K. So we'll take this reaction, okay, and then this has a K of about 170, okay. N2 gas plus 3H2 gas goes to 2NH3. The 2NH3 is called ammonia. And this is at 500 Kelvin. Okay, this is the equilibrium constant is quoted at a specific temperature. So let's say for N2, we'll say we have total volume is 20 liters. Okay, and in N2 we have 2 moles. H2 we have 3 moles. Okay, I'm just throwing numbers here. Okay, so but similar pipeline for the test. What's this? And then 4 moles. Okay. All right, so are we at equilibrium? If we are, good. But if we're not at equilibrium, which way will the reaction go to get to equilibrium? Okay, that is our question. Okay, which way will the reaction go to get to equilibrium? First of all, are we at equilibrium or not? But how do you know this is an equilibrium reaction in the first place? Arrows, yes, very good. Okay, which way will the reaction proceed to establish equilibrium? So this is the question. All right, so the first thing is we'll do the equilibrium constant. Expression is going to be products over reactants. So these are gases, okay, so there'll be no solids or no liquids. But if there's a solid or liquid, you just avoid it totally. And then divided by N2 H2 cubed, okay? So you guys are comfortable in knowing why there's a 2 here, why this is squared? Okay, why is it squared? because of that coefficient. And why is this cubed? Okay, because of that balanced chemical equation, that coefficient. All right, so this is concentration. All right, so let's figure out the concentration of N2. What's 2 divided by 20? Uh, 0.1 mole. What's 3 divided by 20? What is it?
0.15.
0.15 mole? Molar, sorry. Okay, that's 0.15 molar. It's a lot of mistakes in this lecture. I think it's about time for me to retire. Okay, too many mistakes. Okay, molar, not moles. Molar, moles over liter. Okay, NH3 is 4 over 20. 4 moles over 20 liters. What is that, 0.2 molar? Yes, 0.2 molar. Okay, so this is what gets plugged in here. All right, Kc given to us in the problem is 170. NH3 is 0.20 squared. Okay, so this thing is unitless. This K equilibrium constant will have no units. You don't have to worry a single thing about units for K, equilibrium constant K. Rate constant, different story, lowercase k. N2 is 0.10 and H2 is 0.15 cubed. Okay, so if we're at equilibrium, all of this should be equal to the equilibrium constant that they gave us in the problem. Okay? And what is this equal to? 0.2 squared is 0.04 divided by 0.13 cubed. 0.13, I hope this is right, to the power of 3 times 0.10. This looks really crazy on my calculator. Okay, 0.15 cubed times 0.10. You get 118.5. Calculator help. 0.15. Yeah, 118.5. Okay. All right, so doing this on my calculator, I got 118.5, so I think this is the right answer. And are we at equilibrium? Okay, no, because if we were at equilibrium, these concentrations in this expression would equal to the equilibrium constant, which is 170. Okay, so we are not at equilibrium. So that's the first part of this answer. We are not at equilibrium. Okay, we're not at equilibrium. Which way will this go to get to equilibrium? All right, so this is Kc. This is given to us in the problem. You'll see it. So I'm going to call this Q. Okay. Now, according to the Gator rule, we will put Q first and then compare it to K. Okay, there's 3 situations that can occur if you put Q first and compare it to K, and you pretend that this is an alligator jaw. Okay, so Q is equal to K. It would be at equilibrium, but Q is not equal to K. 170 does not equal to 118.5. Okay, Q can be greater than K. Q can be less than K. Okay, we're going to put Q first. Okay, otherwise, what I'm teaching you is all wrong. so Q first is 118.5, 170, and then we can see that Q is less than K. So if Q is less than K, where do the alligator jaws point? To the reactant side or product side? Okay, they're pointing to the product side. So the answer here, we're not at equilibrium. Which way will it shift to get to equilibrium? The side that's to the right, which is the product side. Okay, this is where the alligator jaws are going. Okay, the gator jaws. And this would be a product side. Okay, and that will establish equilibrium. All right, are there any questions or comments on this? Okay. So this is called the reaction quotient Q. We use Q to compare it to K. Okay.
Like the opposite of the radiation, that principle is removed from the scientific class, which is
We're not adding or removing anything.
okay.
This is how it is, and as it is, it's going to move to the right to get to equilibrium. Now, the next problem we'll do, Michael Le Chartier's, it's already at equilibrium. We don't know if it's at equilibrium. Well, we did Q and found out it's not at equilibrium. To get to equilibrium under these concentrations, it will move to the right. In Le Chartier's principle, we have an equation already at equilibrium, and we disturb it, okay, which will be our next problem here. So the equation has already been balanced for you. All right, and they even tell you that this has an enthalpy at standard state. This means standard state. Okay, of about minus 905.6 kilojoules. Okay. So what does that minus sign tell you? Okay, it's an exothermic reaction. So what is also released as an exothermic reaction? Okay, in an exothermic reaction, heat is also released. So the fact that it's exothermic, if it's a negative sign, you have an additional product. Okay. So what happens, and these are all gases, let's say. Okay. So let's say we disturb this system, which is already at equilibrium. Okay, we're not saying it's not, or are we at equilibrium? Which way will it go to get to equilibrium? No, none of that. Okay, we will mess the equilibrium up and disturb this already established reaction. So what happens if we decrease the temperature? Which way will it go? Okay, decreasing the temperature means you are removing heat. So which way will the reaction go? Will it go to the side which has more heat, or the side that has less heat? You're removing it by decreasing the temperature. More heat. So we would expect this to go to the right. Okay. Okay, what happens if you increase the temperature? Okay, obviously if you add heat, okay, it will move to the side to offset that, and this would be the opposite, which would be left, which is to the reactant side. Okay, what happens if we decrease the pressure? So what does decreasing the pressure mean? Okay, will it go to the side that has more pressure or less pressure? Okay, if you decrease the pressure, okay, it will go to the side that has more pressure or less pressure. Okay. So we'll go to the side that has more pressure. So which has more pressure? The one that has 9 moles of gas or 10 moles of gas? 10. So this will go to the right. Okay, it's going to go to the opposite of whatever you do it to it. So decreasing the pressure is the same thing as increasing the volume. Okay. So if it's increasing the volume, it's going to go to the more concentrated. Okay, what happens if you increase the pressure? Okay, will it go to the side that has more pressure or to the side that has less pressure? Less. So this has 9 moles of gas as opposed to 10 moles of gas. So it's going to be the opposite, left. Okay. Okay, what happens if we add oxygen gas? Okay, which way will it go? Okay, it will go to the side that has more oxygen gas or less oxygen gas? Less. Okay. So that would be to the right. Okay. So this is altering the concentration. Okay. What happens if we remove, or how about if we add NO gas? Okay, add something else. Okay, will it go to the side that has more NO gas or less NO gas? Okay, it will go to the side that has less NO gas. And which side is that? Left. Okay. So these are the 3 ways you can disturb a reaction that's already at equilibrium. Okay, you can mess around with the concentrations. Okay, for gases, you can mess around with the pressure. Okay, or volume. Or you can mess around with the temperature. You can increase or decrease the temperature. So this is what we call Le Chatillier's principle. Okay. So that is a Le Chatillier's principle question on the exam.